Hi everybody, my name is Brahm from Learn with Brahm, and today I'm going to be talking about geometrical optics. I'll give a quick introduction to what geometrical optics is. I'll talk about the focal point and the focal length of a lens. I'll talk about the power of the lens. I'll go into the thin lens equation, and at the end I'll have a quick demo, so stick around till then. Let's get started. So what is geometrical optics? Well, simply put, geometrical, or also known as ray optics, is a branch in physics that describes the propagation of light in the form of rays. It deals with light rays that interact with optical elements like mirrors or lenses. Okay, so I've drawn a diagram here, and as you can see there are light rays, and they go through this lens, and something happens to them, and they come together at this point here. So, what's going on? So these light rays, they're parallel to each other. They go through this lens, which is a convex lens, and they refract, or they change direction. And in this case, because it's a convex lens, they converge, or they come together, they meet at a single point, and the point at which they come together is called the focal point. Okay, so that's what the focal point is. Well, what's the focal length? Well, the focal length is simply the center of the lens all the way to the focal point. So this center of the lens here all the way to the focal point, that would be the focal length. Okay, I'm going to use a quick demonstration to show you what optical power really is. So I'm going to turn on my two lasers here. And you see I have two lenses here. One is slightly more thicker and bulgier, and one is kind of slimmer. So let's first take the slim one, and if we have our light rays go through this lens, we can see that they come together at a point around right there. Okay, so now I'm going to quickly swap them out at the same distance, and do you see what happens? Well, now the focal point is here, not here. So if the focal point is closer, that means the focal length must also be closer. Let's go back to the board and see what this means. So what we just saw is we had a thinner lens and a thicker or more curvier lens. And as the light rays passed and traveled through the thinner lens, they had a focal point that was a bit far from the lens. And if you see over here, when the light rays passed through the curvier lens, the focal point was much closer, and so the focal length was a lot shorter in the curvier lens. So this gives us to what optical power is. So the definition of what optical power is how much a lens will refract or bend light. So the equation for optical power is 1 over f, where f is the focal length. So as you can see here, if you have a longer focal length, your power will be less. So out of the thinner and the thicker lens, because there was less distance between the lens and the focal point in the curvier lens, it'll have more power. So now I'm going to talk about the thin lens equation. So the thin lens equation relates the focal length of a lens to an object and its image through the lens. So if you look at this diagram here, I know it looks a bit confusing. You have your object over here, which in our case is a flame or a candle, and you have a converging lens here or a convex lens here, and you have a plane here that has the inverted image on it. So the red rays here, the red lines here, are going through the converging lens. They're converging at this point here. They come here at the focal point, and they continue their path up onto this inverted image. And it's inverted because they land on opposite sides of where they started. So that's basically the premise of this. And so the equation for this is 1 over f is equal to 1 over distance of the object plus 1 over the distance of the image. So f stands for the focal length, which you can derive by measuring yourself. And then the distance of the object is this distance here from the original object here to the center of the lens, plus 1 over the distance of the image, which is the image to the center of the lens right here. So let's say you were given the object distance and you have measured the focal length yourself, you'd be able to use some algebra to solve for the distance and how far you would be able to see the distance of the image clearly. So that would be 1 over f minus 1 over the distance of the object is equal to 1 over the distance of the image. I was able to do this experiment myself, and although it's not perfect, you can still see the concentration of light on the wall in the shape of the fire. And by measuring the focal length and the object distance, I was able to find the distance of the image to be around 4.09 inches. And when I put my measurements into an optical design software, I found that my estimates were pretty close to the actual value. My estimates were only off by a tenth of a millimeter from the actual value, and they weren't expected to be perfect anyways. It's also important to note that the software I was using used millimeters instead of inches. Thanks for watching.